All right, I think we are good to go now. So, chapter, it kind of goes by chapter here. You have the properties, like here the 3 and the M are together, then the 2 and the 3 are, but it's the same order otherwise. So what's been grouped has changed. Do you know what property that is?
I'm sorry, it's cutting out. Distributive?
Distributive would be if you're getting rid of parentheses.
Oh, I see. I probably check my.
Do you have notes organized by chapter?
I do, but I don't. I guess I didn't take very good notes from chapter. I don't have anything with me actually, so.
That's all right. So this first one, it's how things are grouped, meaning how they're associated. So it's associative property. And because it's addition, it's of addition. If it was multiplication, it'd be multiplication. The other property that we test on in this class is commutative. So like home to work and then work to home, like the order changed. You're commuting.
Right.
So you might want to make flashcards that just have those 3 on it, and the key to it is like the grouping changed, the order changed, parentheses are removed, or you're distributing the 5 to each thing.
Mm-hmm.
And then number 2 are the rules for exponents. And I'll go ahead and run through them, and if you have questions or why, or if it's not making sense, and I'll give you a little bit of time to also try them yourself. So maybe I'll zoom in right now a little bit, and you can see if you can do like one, well, I guess A and B.
I don't know. Probably not. I mean, like first person shooters, they don't have.
So for A, what do you think?
Would it? I guess 6x9.
Yep. So you did your 2 times your 3, because that's 2 times, and then that's also 3 times. And so you did your 2 times your 3 is 6, and then you have 5 x's multiplied together, and then another 4 multiplied together, and then they're all multiplied together. So you end up with 9 of them. So don't be afraid of like drawing out the situation.
Right. So on the test, would we need to show that work? Because I just did it in my head. Is that okay?
Yeah, no, that'd be fine. This,
Okay.
There's not much work involved there.
Okay.
Like if you're just adding things together or multiplying things together, you don't need to show work on there. You can show if you want, that it's you could say 6x to the 5 plus 4, and then 6x to the 9 if you really want to show some work that you're adding those exponents. But I wouldn't require work on something like that. It's pretty quick to do. The ones that require work are more like if you're doing several steps.
Right.
But if you're just adding or subtracting some things, that you don't need to show your work.
Okay. Well, my calculator is stuck on. How do I get my T1? Maybe I'm in the wrong one. I still have it. I don't know how to clear it off of the graphs.
On the TI-89? So on the TI-89, you're going to hit the home button.
Okay, there we go. Okay, so this one is B125. Is that?
Yeah, so the negative just made it the 1 over to make it then positive.
Oh, I couldn't see the negative sign.
Oh, sorry.
That's
It is
okay.
not as zoomed in as it could be. That might help too.
Okay. So yeah. So then oh, okay. I guess I wasn't doing that. I don't remember doing that way with the 1 over 125.
Yeah, so whenever there's a negative exponent, you need to change its location from numerator to denominator or denominator to numerator to make it a positive exponent. It's called a reciprocal when you do that. And so because there's nothing else in the numerator, you have to put a 1 as in like a placeholder to put it into the denominator to make it its reciprocal. It's like flipping the invisible 1 and the 5 to the negative 3 over.
I think I remember something like that.
And then C.
X6.
Yep. A power to a power you multiply.
Mm-hmm.
Or you could draw it out by saying x squared 3 times. And then seeing that you have 6 of them.
Mm-hmm.
All right, I'm going to skip down to E, just so we can do a fraction one. It's behaving similarly to that one, but it's a little more involved. So we reduce the fraction, we take care of the A's, and you can either use the subtraction rule, or when you have division with the same base, you subtract the exponents. So it would be A to the 3rd, or you can say, where do I have more, the top, how many more? 3 more. And then the B's, you could either say 1 minus 3 and get negative 2 and then bring it down here to make it positive 2, or you can just say, where do I have more? The bottom, how many more? 2 more. And then one other comment I'll make is when you have parentheses, make sure you square both things. And then on this one, only this factor would go up. The 6 has an invisible positive exponent of 1. So you wouldn't bring the 6 up as well.
Is that 6m negative 2?
Yeah.
Okay.
It's a little early.
Oh yeah, I see this. Okay. Yep. This is awesome. Thank you.
What's that?
I said no. This is really helpful. Thank you.
Good.
Oh, shit.
Why don't you try C on the order of operations on number 3 here.
And then that was, you know, trying to resolve it up.
That's 12 plus 30 equals 42.
You got 42? Good. Yeah, you did your multiplication.
Yep.
Then you did your other multiplication.
Mm-hmm.
And then you got to do your addition. Yeah, it can be tempting to go like, oh, 12 plus 6 and then multiply by 5 if you're going left to right. And it's important to realize you have to follow order of operations and not just go left to right.
Yes.
Okay, the different types of numbers, the different classifications for numbers, whole, integers, rational, irrational. You could have counting in there, which is also known as natural. So do you have any questions about these different categories?
I'm sorry. I lost you again. No, it's something that I'm gonna just read over again and brush up because I don't necessarily like remember everything. So.
Okay. When it comes to rational and irrational, they're opposites. So if you just remember any square root that isn't a perfect square or anything involving pi would be irrational, then everything else would be rational. And then integers are the ones that would be on a number line. So they're positive and negative, but there are no decimals or fractions. And then whole starts at 0 and are just the whole numbers after that. Rational, anything that can be written as a fraction. So that's decimals that terminate or repeat.
Did you say rational numbers?
Yeah, rationals are decimals that terminate or repeat, or fractions. And again, it's the opposite of the irrational. So everything else besides these two, I'm going to put down here. Okay, you're going to see some solving type problems as well, likely involving some distributive property questions. So distributing the 5 and then undoing your addition and subtraction and then undoing your multiplication or division. You'll probably see one involving fractions. And you may or may not be told, since you're doing the online, you get to choose what method you want most of the time. I don't think it tells you. But this one says by the LCD method, which is a nice way of dealing with fractions and decimal problems anyway. So the lowest common denominator between 4, 6, and 3 is 12.
Sure.
So I'm going to multiply each side by 12. You can kind of do a shortcut by just doing 12 with parentheses outside. So this would be the part that you'd want to show your work for your scratch paper.
So 9x plus 2 equals 20.
Exactly. And then solve it from there. And you may have fractions for your answers, or it might be nice integers. Just don't be afraid if you end up with a fraction.
Okay, so x equals.
Right, I don't have any, I'm not objecting. We'll try it. Oh, that's why I like this. So why don't you just follow me?
All right, these are similar. This one, you'd want to get x's together, constants on the other side. And I can combine all 3 of those x's.
Okay, all right.
So 3, 4, 5, and 4x then. And then divide by 4. And if you have time, you might want to write down the problem, work it out, and then check all your work if you have time before entering them all. Just make sure you leave time to enter the answers. Does that make sense?
Yeah, no, totally.
Because I think sometimes, we think, oh, we're not going to have time, let's just get it in, and then you end up with extra time, and you're like, oh, well, I could have checked my work, or oh, I could have done this. So don't be afraid of doing all your work on your scratch paper. Just set yourself a timer to give yourself time to enter.
Okay.
And I know when I was playing around with this, I entered one of the answers wrong. Like I just hit, I don't know how I did it. I hit I think it was like, I wanted to put in 3, for example, and I accidentally hit like 34, and I hit enter, so it submitted it, and I'm like, no, I wanted 3. So that's where the scratch paper comes in, where I'll be able to see like, oh, you really wanted 3, and even though the computer didn't give you any credit, I could go back and give you partial or potentially full.
Right. Okay.
Is-
Yeah, no, for sure.
All right, so then solving for W, you're gonna solve for particular variables. This often happens when you're solving like to put something into y equals mx plus b form for graphing a line. You just, again, undo addition or subtraction. And then undo your multiplication or division. It's pretty forgiving whether you write it like this, because you've solved for W, or you could put it in like P divided by 2 minus L, because dividing both of these by 2, you get P divided by 2, and then the 2's would cancel.
Oh, wait a minute.
Why don't you try to do number 11?
So, I'm not really sure about this one because would it be -4 minus 2 over 3x?
Yeah. You can also do it, the way I did it was I put the x term first, just because I'm used to putting it in standard form.
Okay.
But there it is. There's your -4, and there's your 2/3 x.
Oh, okay.
So, I mean, you could also. It just wouldn't be standard form, but it would still accept it, and it's still a correct answer.
Okay. Perfect.
You'll have some problems where you're dealing with inequalities and doing interval notation and graphing as well. So be careful when you do the graphing that you pay attention to solid or dotted, solid or open dot, and what side you're shading, and that you do it in one nice fell swoop if it's going to the end until you see the arrow.
Yeah, that's a tricky one for me.
If you multiply or divide by a negative, you'll need to switch your inequality symbol, and I just was trying to say that I didn't actually want to do it.
So can you say that again? I'm sorry.
Yeah, if I had divided by a negative, I would have switched the inequality symbol.
Right, okay.
But because I divided by a positive, and I was saying switch it, and so I accidentally switched it.
Oh,
So.
that's funny.
And then for interval notation, when it's got the equal, it's got the solid dot, that's when you use a bracket.
Right.
And infinities always have parentheses next to it.
Oh, I'm losing you again.
Oh, I was just saying the only time you use a bracket is for closed dots. Every other case, you use a parenthesis.
Okay.
They may also give you a problem where there's an interval given to you not as an inequality, but given to you in interval notation, and looking at unions and intersections. It could write it like this, or they may say like x is less than -2 union x is less than or equal to 4. That's what this translates to. So in either case, I recommend that you graph there's one on that white nightstand, and there's one by our bed, I believe. So now I'm going to look at the union. And the union is where you unite them. You combine these two graphs, and when I combine those two graphs, I end up with everything until the 4 being graphed. And so if I were answering this with interval notation, I do that with a graph like that. And if I wanted to give the solution to this as an inequality, I would just say x is less than or equal to 4. And then for, that's union is where you unite them, you put them together. And sometimes when you unite them in their separate directions, their opposite directions, you have to use that U symbol to show it. Let me see if I have an example of that. Not on this particular question.
Yeah.
And then sometimes when you do these, the intersection is, just a section in between. Sometimes it's where they're overlapping but going the same direction, and sometimes there is none, and then you'd have no solution.
Okay.
So just being comfortable with the fact that there's different directions and cases, and you just have to look at whether you're uniting them or you're finding the intersection in. All right, on to absolute value. These next 4 questions are all absolute value. We've got 2 equation ones and 2 inequality ones below. Isolating needs to happen first before you make your 2 cases. Dividing by 2 would give me -3. And now here's an interesting situation, because it's saying this absolute value, which is always positive, equals a negative. And so that's a special case. And you can stop right there and just, like, you can write a positive does not equal a negative would be like explaining why you're saying no solution. If you continued and found values for x, then if you checked your work, you'd discover neither of them actually work out. And so then you could say, okay, no solution.
How did you get rid of the 2 on there?
Oh.
Did you divide the -6 by 2?
Yeah, divided both sides by 2, because it's 2 times that.
Okay, you divided both sides by 2.
Yeah.
And you'll want to make sure that you've read all this out. I mean, what I recall about line ones or the things like that where they were open nodes, essentially.
When you make your 2 cases, so once it's isolated, you can make your 2 cases. I'm not going to solve this, but I'll just set it up. Drop the bars for one case, and for the other case, this distance could also be that it's at -10 on the number line. So like here's 0, 10 away could be 10 or -10. And so this thing in here could either be equal to 10 or it could be equal to -10 to have a distance of 10 from 0. And so drop your bars and change it to its opposite sign for your second case. With inequalities, similar, you isolate first. And then when you make your 2 cases, you drop the bars for your first case. And for the second case, you drop your bars, you switch the inequality symbol, and you switch the sign. So there's 2 changes you need to make when you make your second case for the absolute value inequalities. The other thing you need to know is how are these related to the original problem. And so at this point, I have a great or. So it's either this or this situation. In other words, your distance has to be more than 5, so it has to be over here or over here. See, that in the way. So either this 2x plus 1 has to be greater than 5, that's this one, or it has to be less than, to the left of, the negative 5. That's why you have the two changes. And you solve from there, and you look at, so when you solve this, you get that, and you look at the or, so the merging of the two. And here's the example where when you merge them, you actually have a disjoint section. So you put that little U in there to unite the two segments.
Which problem are you working on?
This one is
Number 18, right?
18.
All right, I just didn't know where the 2 and the negative 3.
Oh, I just said if you continued solving it. I didn't actually solve it, just.
Okay, okay.
And then similarly on that one. And you actually do type in the word or into the XYZ system. You don't type in the word and, because and could be written as a composite thing, and I'll show you one of those. Let's see if I can find one of those.
How do we know if we're supposed to be doing, like, how we're supposed to answer? Does it say in the question? Because there's so many different answers right here. Or or if it's in notation, it's that one.
Yeah, so it'll probably have a box that says like interval notation, and then you put that in. Okay. And then it'll or it might say in set notation, but it will tell you. You won't have to guess. It'll either tell you in the directions or in the answer box, or right outside the answer box. I think it says like interval notation, and then gives you the space for it. And then the graph, obviously, there will be a graph for you to.
Right.
So just like before, you can have special cases with the absolute value inequalities. Here we have a positive, and it's saying that it's less than a negative. So whenever you have a negative with absolute value, you want to stop and think, is it a no solution situation, or everything would be a solution?
Sorry, I lost you again. So you just said whenever you have a negative. That's what I heard.
Whenever you have an absolute value problem with a negative, you need to think about whether it's a special case. So like here, this absolute value, that means it's going to be a positive. Can a positive be less than or equal to a negative number?
Okay, right.
And positives are not smaller than negatives, so this is never going to happen, right?
It's not right.
So your answer would be no solution. If you didn't stop to think about it and you solved it, you would end up getting a situation where it was an and, but there's no overlap. And so you're like, wait, but there's no overlap. Well, that's because there's no solution. So I guess the main point is on absolute value problems, it's not a bad idea to check your work and to show the check. Any other questions about inequalities or absolute value?
No, I'm okay.
So the next topic here is intercepts. And so an x-intercept is where you're crossing the x-axis, and the y value would be 0. for any of those points. And a y-intercept is where you cross the y-axis, and so the x is always 0. So I'll just do one of these. So you solve for the x when the y is 0 for the x-intercept, and you'd solve for the y when the x is 0 for the y-intercept. And I sometimes have students, once they've solved it, this will be 2x equals 12. Dividing by 2 gives you 6. That's 0, so negative 4y equals 12. So y would be negative 3 when you divide by negative 4. I have some students that like to say the answer is like 6 comma negative 3 as like this. Because they think x, y coordinates. These are two different points, so that is wrong. This is an x value when the y was 0. It is the point 60 right there. That's the x-intercept. And then this one would be 0, negative 3. This point right here is your y-intercept. And you can make your line from there. But these are two different answers for the 2 points, for the x-intercept and then for the y-intercept. And I think in the computer it doesn't ask for both like this. It just asks you find the y-intercept and gives you an answer box, or find the x-intercept.
Okay, so we would just put in 0 dash negative 3 then.
Yeah.
Okay.
Okay, then there's some graphing. So it's nice if it's in y equals mx plus b form, slope-intercept form. So this one is, you might be asked to have given an equation like this, just ask, what is the slope? 2/3. What is the y-intercept? Negative 4. Other times they're going to ask you to graph it, and you will need to, in XYZ, only use 2 points. So you could graph the y-intercept of negative 4 and then go up to, rise over run, up to over 3, and plot your point, and it will make the line. If you were doing this on a paper test, it would be a good idea to plot as many points as fits on the graph. But XYZ will just do 2 because they're a computer and they can make their lines perfect.
Could you show how you plotted that just one more time?
Sure. So I started here at negative 4 because that's my y-intercept, so it's a point. So I started here. And then I used my slope, rise 2, run 3. So I'm going to rise up because it's positive and run to the right because it's positive. And then I plotted that point.
Okay, perfect. Yeah, no, I got it.
And if you're uncertain about graphing, you can always go back to a t-table and plug in numbers. It's a little bit harder when it's a fraction. You'd have to, like, if you want to deal with nice integers, you'd have to pick things that are going into the 3 nicely. So you could do like 2/3 times 3 minus 4. The 3's cross cancel. 2 minus 4 is negative 2. So you could plot, there it is, the 3, negative 2 point. And you could plug in 0 is also nice to work with. Then it can come 0, 0. And there's that point. So you can also just do a t-table, but it's a lot quicker if you just know that that's where you start and that's how you move than having to do all this arithmetic.
Yeah, that seems.
So here's again your y-intercept, because it's in y equals mx plus b form. So y-intercept of 1, a slope of 3, which means 3 over 1. So rise 3, run 1. You're likely going to encounter, either with inequalities or equations, a vertical or horizontal line. So here the y is always 4. Who cares what the x is? The y, the height, is always 4. So like x could be 0, y is going to be 4. X could be 1, y needs to be 4. X could be 5, y needs to be 4. because y has to equal 4. So that would be the horizontal line. And I think I shared with you the OIVUX mnemonic device.
Mm-hmm.
So there it is. The horizontal line is the y equals some number. So then the bucks, the vertical line here, the x is always -2. The y can be anything you want it to be. So it's the vertical line, undefined slope, x equals some number. So, you know, on a note card, writing down OIVUX.
Mm-hmm.
And then lastly here, you don't have a y-intercept, but you have a y and an x. So it's not an OIVUX because it's not y equals number, x equals number. There's a y and an x.
Okay.
The y-intercept is an invisible 0. They don't put it there because adding 0 doesn't do anything. So 3x is the simplified version. But it would be starting and going through the origin here at 0, 0. And then the slope is, again, rise over run. So 3 and then 1.
Oh my goodness. Oh, it's not only watch them all the way up front there.
So we haven't done a negative slope problem, but actually this next one is in standard form right now. So we'd want to put it into slope intercept form, or potentially you could use intercepts because 2 and 4 both go into 8, so it would be nice integers. But for practice, let's put it into slope intercept form. So let's get the y by itself. And then we're going to divide by 4. What you noticed here, like I was mentioning earlier, is I put it in standard form. I put the x term first, then the constant, because I want the x term first and then the constant for it to be in slope intercept form.
Yeah, I did that this time.
And it's okay on the other one we were just solving for a particular variable. It doesn't matter. I mean, it's kind of better practice to have it be in standard form, but it will give you full credit.
1/2. Okay.
So now we have a negative slope. So we're going to start at our y-intercept of 2 on the y-axis here. And we're going to go down 1. So I'm going to make the negative go on the top. You can have it go on the top number or the bottom, but you don't put it to both because then it would be a negative divided by negative, which would be positive. And we have a negative here. So -1 would be like down 1 and then run to the right 2 because it's then a positive 2 there. And there's that negative slope. We have -1/2, so it should be going downhill. All right, I'm going to talk about slope for a moment. You might be asked to state the slope given an equation for a line where it's in slope intercept form, so the slope's just the 3. You might be asked to find the slope from a graph, so you can use rise over run, or you can look at the coordinates of those points and use the slope formula, which you'll see later on down on the page. You might have a special case where you have a slope of 0 or an undefined slope. Might be another option you might come across. You might have it in standard form and rewrite it into slope intercept so you can determine the slope. Or as I said a moment ago, you might be given points and calculate the slope using the slope formula, y2 minus y1 over x2 minus x1, and then simplify any fractions you might get. And again, you might have 0 if you have 0 divided by some number, or you might have undefined if it's some number divided by 0. They might also ask about parallel and perpendicular slopes. So parallel lines have the same slope. Perpendicular, you do opposite, so negative to positive or positive to negative, and then reciprocal, so you flip it. So that's like a crash course on the different ways slope can be dealt with.
Okay.
All right. Writing an equation of a line that goes through a certain point and has a certain slope, either because it's parallel to something or perpendicular to something or just plain old given to you like this. This one asks it to be in point slope form. So I would have a note card that has the 3 different forms for the equation of a line: slope intercept, standard, and point slope. So point slope is the one that's y minus y1 equals m.
You said standard, point slope, and what's the other one?
Standard, point slope, and slope intercept.
Slope intercept, that's right.
So this is the point slope. Standard is the ax plus by equals c. Let me move that down a little bit. And the slope intercept is going to have the slope and the intercept, y equals mx plus b. And so here you literally are plugging in your x and y of your point and your slope of 3/5. So y minus 5 equals 3/5 x minus a -4. And don't get it out of this format because the problem asks for it like this, but you can simplify the double negative as a positive.
And this point slope, okay, I don't.
Yeah. So it's in that format. You could, if it asks you for slope intercept, distribute and get y by itself, so it looks like this. But it doesn't ask you in this particular problem. But if you were asked, you could always do that, distribute and then get y by itself.
So I'm sorry, back to that one really quick. You just put like an x and a y for the -4.
5.
So I was just trying to figure out how that was set up.
Yeah, so if this is our, I could even put a 1 there. It's our one and only point. When we have equations, we want to have an x and a y, and so we don't fill it in for the y, we fill it in for the y sub 1. It's the one and only point we're given. And if you're given 2 points, you just pick either one. So I plugged it in. When you do, when you do point slope form, you literally plug in your point value and your slopes.
You'll have better defense than me.
It's kind of a weird format. You don't see a ton of, but it's something that gets used in calculus as well. It's just really convenient to be able to say, well, this is the equation of a line. It goes through this point. There it is, and it has this slope. So it's just a quicker way of writing an equation of a line. If you distribute and get y by itself, you'd be able to put it in the slope intercept form or standard form if you got it into that format.
Okay, it's x1 and y1. I understand it now.
Yeah, I know it's kind of weird because we write x, y, but it's when you're in that context, it's plugging in for the x sub 1 and the y sub 1. All right, inequalities. Graph the boundary line. Either it's a solid or dashed boundary line. If it's greater than or less than, then it's dashed. If it's greater than or equal to or less than or equal to, then it would be a solid. So this one's going to be dashed. And
that is not what I wanted to put.
And again, you only do 2 points for XYZ, pick the dashed line, and then you're going to toggle to whichever side you want to have shaded. And so the way you determine that is by testing a point, such as 0, 0. So if I test 0, 0, I'd have 0 greater than 3/2 times 0 minus 2. Anything times 0 is 0. So I get 0 greater than -2. Is 0 greater than -2?
I didn't realize that was even an option. Okay. That's the energy story. Find that out.
0 greater than a negative?
I'm sorry, you're cutting out.
Oh.
I'm getting like a little bit, but not everything.
Is 0 greater than a negative?
Yes.
And so because this test point 0, 0 was true, it means that is a solution. So I'm going to shade that side. If it was a no, then it would not have been a solution, and I would have shaded the other side. So that's how you graph inequalities, is dash your solid line, and then you test a point to see what side to shade.
So yeah, that's the part that I'm really struggling with, is how to test to know which side to shade.
Okay, let's do another one. Let's do let's do this one because it's got other concepts to review also. So I would get y by itself. So I'm going to subtract 3x from both sides. Show it right here. And then divide by -4. Since I'm dividing by a negative with an inequality, I switch the inequality symbol.
Right.
And then I'm going to graph this boundary line. So starting at -3, the y-intercept, then going up 3 over 4. Again, this one is a dash because it doesn't have the equal sign.
And then we're going up 3. And over 4.
Is that you go with the mass storage? I mean, energy storage.
So here's where the testing comes in. You can test in the original because that's the line you've graphed, or in this one that you've modified to put it into slope-intercept form for easy graphing. But if you forget to switch this inequality, then you'd be testing something that's not equivalent. So I always recommend that you test with the original problem so that if you make a mistake, you're not testing in something that's wrong. So I'm going to test the point 0, 0. So I'm going to plug in 0 for the x and 0 for the y. And I'm going to see what this gives me. 0 minus 0, so that's 0.
Oh, okay.
Is 0 greater than 12?
No.
And so this time, this test point 0, 0 was not a solution.
Okay.
And so I'm going to shade the other side.
Okay, I get it. That's so easy. Okay. I was really...
Oops, I think you cut out this time.
Oh, yeah, that's super easy. I was overthinking it. That's so simple. Okay.
Okay, great. All right, and then there's domain and range.
Mm-hmm.
If it's in a list, domain are your x's, and it's just a separate, distinct x's. Your range are your y's. And you don't need to duplicate, so I didn't need to say 1 twice. And you can determine if it's a function by making sure that an x only goes to one y. So 5 is only going to one thing, 6 is only going to one thing, 2 is only going to one thing, 8 is only going to one thing, and that's because they're all separate x's. So the only issue is like if you had an example where you had an x of 2 going to 1 and you had 2 going to 5, that would not be a function. Because an x went to 2 different things, and an x of 2 went to 1 and it went to 5. Another trick is to plot these on a graph paper and see if it passes the vertical line test, which is what I can do on this one, is make sure I'm only touching one point at a time, which I am, so this is a function. But here we don't have distinct, we don't just have 4 points, we have every single point in between these two endpoints. And so the smallest x we have, the lowest it goes, the most left it goes, is -5. And it's got an open dot there, so parenthesis, and then it continues until you get to the x of +4 with a closed dot, so a bracket. So because it's continuous, you use your interval notation. And then your range, your smallest y, is -2 with an open dot. And your largest is 3 with a closed dot, so bracket.
Because -5 isn't even like in that list.
Oh, this has to do with this graph.
Okay, we're on a different, okay, sorry.
And then just to practice some function notation stuff, f of 6 means your x is 6, and then that's your input. So when you plug in 6, what do you get? Well, if we plugged in 6, we got 9 as our output. So it's kind of like x, y.
I lost you again. Oh. Yeah, I'm sorry. So the F6, yeah, I was wondering how you did that.
So f of x, this is your x, and then it's when you plug in an x of 6, what do you get out? Well, when you plug in an x of 6, we got out 9.
Oh, right. Okay.
So here in the graph version, instead of the ordered pairs, g of 4 means an x of 4. So when I go to x of 4, the point I get out has a y of 3. So again, it's like x and y coordinates. This domain keeps going left, keeps going right because of the arrows to infinity, well, negative infinity and then positive infinity. The range is your lowest, so 3, and it's got a solid dot there, and then it keeps going up and up and up and up, so to infinity. And then it passes the vertical line test, so it is a function.
Passes the vertical line test.
Oops. Let's see. And then the last major topic is going to be function notation. And we've done a little bit with talking about this a moment ago. F of 5 means your input is 5. Instead of an x being here, it's a 5. So when I go to my function here, instead of having an x, I'm going to have a 5. So I'm going to have 2 times 5 plus 3, and I'll figure out what that value is. Or here for G, I'd plug it in and do -6 squared minus 2. I'm plugging it in for the X.
Right.
I think we were talking about doing like a blob or something, weren't we? No, that was someone else who wanted help on Thursday. Never mind.
I think, yeah, I think I got this, I think.
Okay. And then you might have composites where you start on the inside and you figure out what G of that is first.
Yeah, I think those are the ones that kind of get me.
So I'd start on the inside. G says, take what's in the parentheses. That's what X means. It means what's in the parentheses because that's what was in the parentheses. Square it and subtract 2. To square, you'll end up doing FOIL.
I lost you again.
Which you would have had in a prior math class, and you're going to see again later in this course. So it might be a little bit trickier if it's been a while and you're not to do FOIL, but there's what that would be. And I might not have you doing much foiling on your test.
I can't see the problem. It's like, I think the picture
Oh,
cut out a little bit. So it's just x plus 3 minus 2, and then you did there's an exponent.
yeah, so it's x plus 3 squared minus 2. Is this better?
Yeah. Yeah, I can see it now. Yeah, okay. We just did this.
Yeah, and then once you find that, now you can do the f of whatever that was, which was x squared plus 6x plus 7. And the f now says let me bring it back over here so we can see it, do 2 times what was in the parentheses and then add 3. So I'm going to do 2 times this, and then I'm going to add 3. And so I distribute and add 3. There's one other thing that sometimes people have a hard time with, and that is like a problem like I, where they think that they're multiplying by -2, or like this one that they're multiplying by 2, but you actually need to expand this arithmetic problem and then evaluate. So you're not multiplying these functions by 2. That is the input. It's f minus g evaluated at 2.
Mm-hmm.
So that's really the test prep, and we're just over 7 o'clock at this point. So the systems of equations material, if you want, I'm happy to continue and go through it with you if you have the time.
I don't want to take your time. I'm sure you're busy.
Well, I'm gonna have to do it at some point, so it doesn't matter if it's now or.
If you're doing it, I will listen.
Okay. Let me go get a blank copy of it. All right. So it's just 4-1 and 4-2. And 4-1, you're going to have some graphing of systems. And what that means is the answers, the x and y values, need to be true for both statements. And so to be true for both statements, this point where they would intersect would be true for this one and true for that one. And so it's about the point of intersection. and you've done other graphing and rewriting before. So all it is graph it to see where they're intersecting. Then we also have elimination and substitution methods for solving. And the idea behind elimination is that you line up your x's, your y's, and your constants, you put them in standard form, and you try to eliminate either the x's or the y's through addition. So if I add these two equations together right now, the y's are opposites, and so they will be eliminated, and I'll end up with 5x equals 10. Dividing by 5 gets me 2. So I know that I'm somewhere going to be having an x of 2. I need to find the y, though, that goes with it. So I go back to either one, because it has to work for either one of these. It has to work for both of them. So I go to the one that looks easier to me, and I plug it in for that variable. So I plug it in for the x. And so I can solve for the corresponding y value. And so the point of intersection is an x of 2, a y of -1. And because we're talking about an ordered pair of x's and y's, we list it like that as an ordered pair. So it's always x comma y. Sometimes we're not so lucky. Like this one, the y is eliminated just by adding. Sometimes they don't. So we look at the x's, we look at the y's, and we see how can we multiply the entire equation to make it equivalent in such a way that the x's or the y's are opposites. So if I wanted the x's to be opposites, I could multiply this by -1. Or I could have multiplied the top by -1. It doesn't matter. And so now that I've done that, I have opposite x's, and they will cancel. And I can solve for y. This time I solve for y first, and so when I go to plug it in, I'm plugging it in for y and solving for x. And again, either equation, whichever one looks easier to you to work with. I'll go ahead and do it on the bottom one because it's slightly smaller numbers. Maybe you prefer the top one because there's more positives. It's up to you. Plugging in for the y, and you're going to solve for the x. And so then it's x comma y. And I'll show you one more, just the start, and I won't finish solving it, where we need to do a little manipulation. So we could get the x's to be 24 and -24, or we could get the y's to be 14 and -14. That's the quickest because all I need to do is multiply the bottom by 2. So you look for the lowest common multiple is what you're trying to either get your x's or your y's to be. It's the smallest equivalent that will eliminate your variable. So look for the lowest common multiple of your x's or your y's. So sometimes it just is ready to go. Sometimes you multiply one of the equations. Sometimes you need to multiply both equations. Like here, I need to get it to be 15 and -15, or 12 and -12. And so it'll require both equations to be multiplied by something. So if I decided 12, because I think it's smaller than 15 and I want to work with smaller numbers, I could do 3 here, 2 here to make both 12, but then one needs to be -12. So make one of those negative, and one will now be +12, the other a -12, and the y's would eliminate. Does that idea of multiplying equations make sense?
It does.
Okay, and the only thing that trips people up typically on these is forgetting to multiply the constant also. Like they, you know, a lot of students go negative 12x minus 14y, and then they say equals negative 10, but it actually would equal negative 20. So just making sure to do it to every term to keep it equivalent is the trick. Substitution is when you have it not in standard form and it's like y equals something or x equals something, and you just plug that in for the variable it represents, and you'll get an equation with just one variable then. So you can solve for x, and then once you have x, you can plug it in and solve for y. Substitution, you kind of do it intuitively. In the past, you've already done substitution problems, and now it's sometimes gets harder because you're asked to do it, and so you're like, wait, it seems new, but it's not something you've already done before. And then last is for that idea is that there might be special cases, and I kind of have an example pre-worked out here. You might have a dependent or inconsistent system. Basically, it could be that your two lines are really equivalent, and so there's an infinite number of points of intersection. They're always intersecting, and so you have infinitely many solutions regardless of what you put in for your x or y. You're going to get an answer. Versus inconsistent is when they're parallel and there's no intersection, so then there's no solution. And when you go to solve these algebraically, you either get a true statement, so that would be infinitely many solutions, or a false statement, and that would be no solution. So this is kind of my key in terms of the algebra of it, the graphic, and that's, again, when the x's and y's both cancel, you get the special cases. And then after you're comfortable with systems of two, which is from an algebra course, the new topic for an algebra 2 or intermediate algebra is a system of three equations. And so this is likely kind of new to you. This is probably review, but the systems of three is probably new. So with a system of three, you're given three equations with three different unknowns, and we can't handle that. So what we do is we take two at a time and get rid of the same variable. So either you get rid of x's, y's, or z's for two pairs, and that creates then a system of two, which we now know how to deal with. So the idea is go from your system of three to a system of two. So to get a system of three to a system of two, you have to get rid of the same variable. I chose to get rid of y's in this particular example because they're already opposites here. I didn't have to multiply by anything. So I was being strategic in getting rid of my y's. So I paired up equations 1 and 2 to get rid of those y's, and then 2 and 3 to get rid of the y's.
So in the one that I was doing before, it seems like they got rid of the y's and then they went and got rid of like something else in the video that I was watching. So you got rid of the y's in all three equations before you moved on.
Yep. So I got rid of the y's by pairing up. So basically here's my directions. It says pair two sets of two equations. So I paired 1 and 2, and then I paired 2 and 3. And it says to create a system of two equations with the same two unknowns. So the idea is that you need to eliminate the same variable, like y's with 2 of them, and then y's with 2 others from your system of 3, so that you have just z's and x's. So it's a system of 2. Because if I got rid of y's here, and then I got rid of z's here, then I'd still have x, y's, and z's to deal with. So the key is eliminating the same variable with the two sets of two equations. And I'll show you another example, but So once you've gotten rid of the same variable with two different pairs of equations from your system of three, then it's like solving your system of two like we were just doing. This one was nice because they were already opposites, so it was quick to find x. I plugged it in to find z. And once I have the two letters of the system of two, I can go back to any of my original equations and find that third variable, in this case, the y. And so I plugged it in. I plugged it into the second one because it looked easier, and I found y. And if you like, this version of it, I can email you this page too, if you want to look at it a little bit more carefully later.
Yeah, if you wouldn't mind, I really appreciate that.
So let's look at a few more just to get the idea behind it down. So here's my 3, and I'm noticing that I have opposite y's. I don't have opposites of anything else. So that would be pretty quick to eliminate the y's. So I'm going to eliminate y's. So I made that decision. So I'm going to pair up 1 and 2 to eliminate y's. And then I'm going to have to pair up 2 others to also get rid of y's. So I might pair up the middle one here, multiplied by 2 with the bottom, so that I'd have negative 2y and 2y. And that's what I did here. I wanted to get the y's to be opposites, so I multiply by 2. So I'd have negative 2y and positive 2y when I did the multiplication, and so my y's canceled. So I got rid of y's with equations 2 and 3 and equations 1 and 2. So my system now are those two equations where it involves just x and z. And there's just a lot of writing going on, so I like to kind of make it clean. So I now say, okay, now I'm solving the system of 2. So I write my system of 2 that I just generated, and I solve that. Once I've solved that system of 2, I go back to any of my original equations. I went to equation 1 because it looked easiest, and I found the third variable. So I think it takes some time to digest and see how this all works. So I'm going to send you the whole document where it's all color-coded.
Yeah, that'd be so cool. Because if I can just like work through it and follow along, then I like really like understand it.
Go ahead.
I think the ones with the I'm sorry. I said I got some of them done, but I think there was one with variables where none of them matched.
Uh-huh.
That's where I got stumped.
So that's probably kind of similar to this example. So the x's, the y's, and the z's don't match. And so I can look at the x's and say, what is the lowest common multiple? And it would be kind of large. Here would be 12, and here would be 6.
Yeah.
So I decided to get rid of the z's using 6 and negative 6 as my coefficient. So to do that, I could multiply by negative 3 and then use that positive 6. So I made this negative 6, and I used the bottom one positive 6. And then I multiplied this one by 2 to make it negative 6, and I used the positive 6.
Something else was.
And so that got rid of the z's. And so now I have the system of 2. I call them equations 4 and 5. The system of 2, and it's not as pretty as the other ones. Like the x's aren't opposites, the y's aren't. I have to multiply both by something to get them to be. So the lowest common multiple is going to be 42, and that's getting rid of the y's by doing negative 6 and 7, or you could do 6 and negative 7. You just need them to be opposites. Versus if I try to get rid of x's, it would be a much larger number. So I try to be strategic and find the lowest common multiple and then make them opposites.
Mm-hmm.
And solve for x, plug that into one of the systems of 2 to find the second variable, then go back to the system of 3, one of the original ones, to find my third variable. So the process is go from a system of 3 to a system of 2. Solve the system of 2 and go back and solve that system of 3.
Got it.
And they do take time and they do take space. I mean, every problem takes me about half a page.
Okay. Takes me a whole page.
And it can be really frustrating because if you make a mistake with your signs, like you forget, or you make a mistake with your addition, like maybe you accidentally said negative 15x plus 3x was a negative 11x, then everything else is going to be wrong.
Yeah.
Or if you accidentally said that this would be positive 1 here instead of negative 1, well then because you're using it, this would be wrong. So you just need to go slow and take your time and make sure you're doing your arithmetic correctly. There is a way where you can actually determine the answers with your calculator before doing it, so you can avoid making mistakes early on. Like you can get your answer in the calculator and then you can say, oh, it needs to be 8, and if you accidentally got like 9 or negative 8, you did a mistake before you kept doing more wrong things. But it can be a little bit tricky to teach the calculator too. So I don't want to teach you a new thing right now. So that's basically it. The weird thing is if there's zeros, people think it's harder. It's intended to be easier, but it's just weird looking. So I like to put them in so you can more clearly see what you want to get opposites of, and like, oh, I've already gotten rid of z, so I could get rid of z's just by multiplying this by 2. Or, oh, I already have no x's here, I could get rid of the x's by multiplying by negative 1. Or, oh, I already have no y's here, I can get rid of the y's by multiplying this by negative 2. So basically, one of your systems of 2 is already pre-done for you, so it's actually less work, but it seems harder for a lot of students because it's different.
Okay.
So I'll send that one also. And this one is an example where when you try to get rid of either x's or y's or z's, it actually turns out that all of them go away, and so then that's no solution. Because again, it's a false statement. If this had been like 0 equals 0, it would have been infinitely many solutions. So it's the same rule as we had for the systems of 2. And then we'll get more practice in the next week when we do some applications for it, and I'll teach you 2 other methods. One is Cramer's rule, and the other one is Gaussian elimination. And then that will kind of conclude your lesson on systems of equations. And then there'll be one section on systems of inequalities. So you'll get back to the whole graphing inequalities, but you'll graph 2 of them on the same graph and look for the intersection of the shading. So that'll be next time.
Yeah.
All right. If you have any other homework questions, feel free to ask.
Thank you. I wrote down a couple numbers. I think it was 3, 5, 6, and 7, but I don't need to go over all of them. There was just some. I think it was x plus y equals, or they just the 3 terms, they didn't match. So there were 2 that were. There was one that was like x minus z. One was y